Okay, let's start our class on chapter 5 on elements of plasma kinetic theory. Well, in in the previous chapters 2 and 3 and 4, we studied the behavior of charges, individual charges in prescribed electromagnetic fields. But now, since in plasmas we have zillions of particles, then it's too difficult to study the individual behavior of each particle. You would have to have a very powerful supercomputer to produce simulations on that. Sometimes people do something similar to that. But usually, if you want to know the behavior of particles, you'll probably prefer to study the distribution function of the macroscopic variables. So you will divide your space in regions, in small regions, small boxes, and you'll have a distribution function for the behavior of the electrons and ions in those boxes. And then you can write an equation, an ordinary differential equation for the distribution function. That's the Boltzmann equation. And that's what we're going to do now. We're going to introduce some basic ideas about plasma kinetic theory, and then we'll derive Boltzmann's equation. We'll work in a phase space, a three-dimensional phase space, with the position vector r for the particle position. So we'll represent this vector by three components, x, y, and z. And we'll also work with a velocity vector. So we have a position vector. The velocity vector will have the following components: vx, vy, and vz. And these are basically the time derivatives of the components of this vector. So we have both a position vector, and we could just change r by v and have a similar three-dimensional visual representation for the velocity vector. So our phase space, the phase space, we will adopt a six-dimensional phase space. The first three dimensions representing position, and the following three representing velocity. And the trajectory will be just the trace of a curve of the particle motion in this phase space. So obviously we will not be able to draw a six-dimensional phase space, but you can plot projections. You can plot different combinations of three-dimensional coordinates of this six-dimensional space. For instance, you may plot the evolution of the position, plotting x, y, and z, or velocity, or you may have combinations of x, vx, and vy, depending on what you want to see. But this is basically the phase space we'll be adopting in this chapter. The state of the system will be just the state of the system will be represented by, if you have n particles, for instance, then you have n points in this phase space representing the state of each charge. And we may define some elements in this space. We have a few volume elements. Let's define d square r as this element. This is not like in calculus when you have an infinitesimal element with dx going to 0. In our case, dx will not go to 0 dy or dz. It's just going to be a finite element. It will be big enough to contain many particles and small enough to be small compared to other scales or variations of temperature and density. Like, for instance, if you have a gas with n equal to a density of 10 to 18 molecules per meter square, and you have D3R, it could be something like 10 to minus 12, for instance. It doesn't have to go to 0, the volume. Then we would have 10 to 18 times 10 to minus 12. That'll be 10 to 6 molecules per volume element. Okay, so molecules per volume element, which is still a large number. So you may have a small volume like this, 10 to minus 12 meters square, but still have, depending on the density you're working with, you still have a large enough number of molecules. For us, you would like to have dr larger than the bi length, okay? We'll have also another volume element for velocity. It will be dvx, dvy, and dvz. And in our space, volume element, a full volume element, will be a 6D cube. So many times we'll work with this volume element, which is just the product of everybody. Okay. Now let's talk about the distribution function. This is the most important variable in our system, distribution function. In kinetic theory, everything goes around this one concept. Let's first define what is d6 and alpha. It's a function of position, velocity, and time. This is just the number of particles of alpha particles, actually, because in the plasma we'll have more than one particle. We have all sorts of ions and electrons and neutrals, so number of alpha type particles. Number of alpha in a volume, and d3r, d3v. At position r and v and instant t. So this is one of the variables that we'll use a lot in this chapter. The other one is the distribution itself, f alpha. Also a function of position, velocity, and time. And this is just d6 and alpha rvt over the volume. Don't get messed up with the numbers. Sometimes I follow the book's numbering system, so this is in the book it's 3.1. So f alpha is the distribution function in the phase space. In this case, so the distribution is just the density of alpha type points in the space. Density of alpha type particles in the space. That is the number of alpha type particles in position RV in the element and the volume element in position RV. But this is divided by the unit of volume, dr square, dv square. Okay. And we'll consider that this is a continuous function. Although you may say, well, but this is just a counting number, so it should be a discrete function because you're counting particles, so you have actually a discrete number of particles in each volume element. It could be the case that it doesn't change continuously. You could have a certain number in a position, and a different number in the next position. But here, actually, since we're talking about gases, that they behave according to diffusion and other phenomena. So this is most likely be a continuous function. So we'll always consider that it's a continuous function. Therefore, you can integrate it. Okay, so this is an integrable function. In a volume with large velocity, suppose you have an element, a d3, an element like this, d3r, d3v element, with large velocity. Then you expect the density to be, the number of particles to be small. You expect to have small number of particles with high velocity in each volume elements. Why? Well, because, well, this is basically how gases behave. So we'll have F going to 0 as V goes to infinity. So I have a very small number of particles with very large velocity. And it goes to 0 if velocity goes to infinity. We'll say that plasma is homogeneous if F alpha does not depend on position. Okay, so this is a homogeneous plasma. F is the same in any position. We'll say that a plasma is isotropic if F does not depend on V, on the velocity. So it's isotropic. It may depend, although it may depend, and it usually does, on the modulus of V, okay? But it does not depend on the direction. The direction of V will not affect the distribution. So the number of particles flowing in a given direction is the same as the number flowing in the other direction. So that is an isotropic plasma, okay? So those are two important terms in the plasma subject. And plasma is in thermal equilibrium. If what? If it is homogeneous. It is homogeneous. Isotropic. And time independent. Okay, so those three things, that means that the distribution doesn't change with time, the distribution f of alpha. So that is a homogeneous, a plasma in equilibrium, in thermal equilibrium. Now let's define a few other quantities. The number density and the average velocity. So the number density is an alpha, it's a function of just position and time. It's defined as d3r, the position part of the volume, integration in v of this quantity. Okay, so we are integrating this quantity, which we have defined here, the number of alpha-type particles. The number of particles integrating in velocity, so we'll end up with just position and time as variables, and dividing by the volume element. So if you use 3.1, so we'll just rewrite this equation using 3.1. So it's this times this. We can rewrite it like 1 over d3r v f alpha rvt d3r d3v. And in this case, we can just cut this off here. There's no problem in doing this operation, and although this is inside the integral, because the integration is in v, not in r. So I can just move this out of the integration and cut with this. And now we have this representation for the number density. So two equations that you may use for this quantity. One is 4.1 or 4.2, and this is the number density. I've used 3.1 here. Okay, how do you write 4.1 in coordinates? Because this is just one integral, it may confuse you. But this is actually three integrals because we are in V has three components, right? So if you want to write all components, know that 4.1 is actually this 1 over, what is this? Well, let's write all components. So we have dx, dy, and dz. And then we have three integrals in v. So this is, well, let's write this one, right? I could just have used this equation of 4.2. Actually, let's write 4.2, not 4.1. 4.2. Let's write 4.2. 4.1 will lead to 4.2, and so 4.2 is just the integral in v. So integral in v is the triple integral for f of rvt times, well, the d3v, dvx, dvy, dvz. And what are the limits of the integration? Usually we'll use the limits from minus infinity to plus infinity. We want to integrate this in all possible velocities, because you may have some particles with very high velocity of, in positive or negative direction. So you want to include all particles possible. So of course, most of them, no particle will have an infinite velocity. So most of these integrals will be zero, but some of them will not. So we just write it this way to include, to not miss any particles, right? Now, we have all these definitions. How can we use them to compute useful quantities like, for instance, the average velocity, average particle velocity, so mean particle velocity? The mean particle velocity will be defined based on these equations as this. You have, let's denote it by u. Function of position, sorry, velocity as well. No, just that's right, just position and t. It's mean velocity, of course. So we'll write. Well, we have the equation for the distribution. We just multiply this equation by the quantity we want to compute the average. So in this case, we want the mean velocity. So we multiply it by v. So it's v times f of r, v, and t, d square v. And this integration is, of course, in v. Over, we divide it by this. Or you may want it using 4.2. Where is 4.2? 4.2 is this. So we may call this the n, right? So this is n. So the denominator is just n. N alpha RT. Now, if we take this and use, it may be useful to use again 3.1. Let's use 3. Where is 3.1? 3.1 here. So what I'm going to do now is to write f as this fraction over here. So using 3.1, you have this as the v integral of v d6 and alpha rvt d3v over d3r d3v, and this over n. Now I can cancel this with this, and I end up with this expression for the average velocity. So let's write it this way. U alpha RT became 1 over n. Well, I can just remove this from the integral because integration is in v. This is not a function of v, so I can take it out, d3r, and now this integral here, d6n rvt. This is 4.4. Okay, so this is an important expression. We will use it in the future, so let's circle it. Okay, so this is the mean particle velocity. So basically we are taking all the particles, this is just counting the number of particles in this volume element, multiply it by V and integrate in V. So I'm counting the number of particles with V velocity at this position and multiplying it by V. So this is the sum. Then we have to divide by the number of particles in this volume element to get the average. In a general sense, we may write the average like this. In general, the mean value of the quantity x in the velocity space is given by this formula. So this is representing the mean value of x is equal to, you will integrate the distribution function times the quantity we want. You integrate in V, and you divide by the distribution in V. Let me write it this way as well. Okay, this is just the number density per unit volume of an ordinary physical space. Okay, now let's talk about the Boltzmann equation. Let's try to derive an expression for the equation, a differential equation for the distribution function in the collisionless case. Let's consider that there are no collisional effects. So if you have an alpha particle in a given d3r, d3v element at position rv, and suppose there is a force, an external force F being applied to that element, then in the absence of collisions, in the absence of collisions, and in the presence of a force F, you have, well, you have a change in the position of particles according to this. Well, you may represent the derivative by this finite difference. So this is just the definition of a derivative. Usually you would have a limit of dt equal to going to 0, but not now. I'm removing the limit and considering finite dt. Then I have this approximation for the derivative, and this may be written like this. I apologize for the noise. There's a background noise of children. I'm near a school today and they're very noisy today. So I have RT plus dt. I'm just solving for this. So this is dt times dr dt, but dr dt is just v, right? So we have the velocity times dt. And the same for velocity. The velocity also changes according to this. Or just let me write it straight away, that we have v of time dt is equal to, for the same reason, same approximation, you'll get this one, right? 5.2, where I'm using A equal to dV dt. Okay, and also I may write a like this. Force is mass times acceleration, and here I'm using the mass of the alpha particle, right? And I will adopt this notation here, that r prime be equal to r of t plus dt, and v prime will be v at t plus dt. Sometimes I use this, sometimes I'll use this, right? For the same thing. So if I have a number of particles in an element dr3, dv3 at instant t, they'll occupy a different element. So you'll be moving from particles from this element to another one. Oh, sorry. This is prime d3v. Okay, so we'll be moving from an element to another one based on these relations, and we'll try to figure out an equation for that. In the absence of collisions, again, so this represents time t, and this represents time t plus dt, right? The shape of the element may change. You may have a cube here, and it's deformed into something else after some time, because you're integrating all particles in this cube, and so you don't know what will be the shape of this after dt time units. But you will have, for the distribution function, you'll have this. You have the distribution at time r prime, v prime, time t plus dt. In this element will be the same as in this one here. So this is something that we'll take as a fact, that you don't lose and you don't gain any particles, okay? So the number of particles will be the same as the number of particles. This is basically the number of particles, right? This is d6n alpha of this. So you don't lose, you don't gain particles if you're not considering collisional effects. No loss or gain. No loss or gain if there are no collisions. Okay. But you know that the shape of the element will change with time, and it will change approximately by this amount. The volume the new volume d3r prime d3v prime will be this quantity times the original volume. What is this? This is the Jacobian. You know this from multivariable calculus. The Jacobian determinant. So if you deform a shape of an element by some function, then this is the Jacobian of the function times this the original volume. it may be expressed like this. The Jacobian is this derivative. Sometimes they use this notation as well, which is a determinant. This is actually the modulus of the Jacobian. J as the Jacobian, this is the modulus of the Jacobian determinant. The determinant is this one. So you have, let me put it explicitly in case you don't remember how to compute this. This is just this. You have the derivative of all your new variables in relation to your original variables. Okay, so you may write it this way. It's the derivative of x prime in relation to x, then y prime in relation to x, and everybody in relation to x. Then you have x prime in relation to y, y prime in relation to y, everybody in relation to y, and so on and so forth. Then finally you have the derivative of everybody in relation to Vz. Okay, this is a determinant of the Jacobian matrix. This is determinant. But this is not a determinant. This is absolute value. The modulus. Okay. So for those who didn't remember it, here is the Jacobian. Okay. So this will measure the change in the volume as you apply a linear function to some other volume. Okay. So actually we're measuring the deformation caused by a linearization of the function. And I forgot to put the number for this one. This equation is number 5.4. Is that it? So we had that 5.3 and this is 5.4. Okay. Now, it is possible to show that this determinant is 1 in this case. Okay, so J, the modulus of J in our context is 1. Let's just write this. It is possible to prove that modulus of J is equal to 1. This is in section what is this section? Section 5.2 of the book. If you're considering what? You're considering that if the force is composed of two parts. The first part we'll call F prime plus the second part, which is just Q, the charge of the alpha particle, times V cross B. This is from Lorentz force, but now we have a part that is independent of V. This part is independent of V. This is not. This is the independent part. Like if you're using Lorentz force, then you have just this, right? Then if you use this F prime, then you get Lorentz force in the traditional form. Now, if this is true, supposing that this is true, we have read section 5.2 and understood it, then you have from this equation from 5.4, then from 5.4 you get d3r prime d3v prime equal to d3r d3v, right? Then you can rewrite 5.3, take this expression here, then we can equalize this to this. So we may just write everything in terms of this. So 5.3 and from 5.3 you get f r v prime t plus dt minus f. I'm just joining these two terms here, multiplying them by this, and this is equal to 0. Now let's expand the first term in 5.6 in a Taylor series around f of RVT. So expanding the first term around f alpha RVT, you get, well, this vt plus dt will be equal to, let me see, maybe just leave it this way. I'll have, no, this is okay. So this is equal to, let's expand it. So the first term is just this, RVT plus the derivative. I'll write it just up to the first order. So I have a derivative in relation to r, then in relation to v, and then a derivative in relation to t. These are the first order derivatives. Derivative in relation to r, the position, then it's a gradient, and I'll write this gradient like nabla r, just for us not to confuse things. So I have nabla r times what? Times r plus vt, which is here, this one, r plus vt, minus r. So we end up with just v dt, right? So this is, this is v dt. This is a vector dt. Then we have derivative in relation to v. Times what? Second one is v plus dv. Yeah, v plus a dv dt, which is a dt, minus v. So we end up with just a dt here. Plus the derivative in relation to time of dt, plus higher order terms. Okay, in this case, if we drop the higher order terms, we end up with just, well, let me see, this is 5.7. Just move this to the left. So I have R V t plus dt minus F R V t equal to, well, I'll start with this part here. Everybody now has a dt here, so I'll leave dt in evidence. So I have df d del f del t plus this is v dot nabla v. So it's v dot nabla r f. And here it's a dot nabla v f dt. I'm dropping higher order terms in the Taylor expansion, just keeping the first order derivatives. Now I'll use 5.6. I know that this is equal to this, but this is equal to 0, so I can say that this is equal to 0, right? Using 5.6, I say that this plus v r v t plus a v f r v t is equal to 0. And this is Boltzmann's equation. Boltzmann equation. In the absence of collisions. Oh, sorry. Absence of collisions. Sometimes they may write it like this: df dt is equal to 0, where d dt is del t plus v. This is the total derivative. Total derivative. In relation to time. From this form of the Boltzmann equation, you can see that the distribution doesn't change with time if you don't have collisions. Of course, if you're in the reference moving, in the frame moving with the element of fluid and the phase space, which is what this notation represents. And this is sometimes called Liouville's theorem. And here you don't have collisions nor radiative losses. In the absence of collisions and radiative losses. Well, Boltzmann equation actually doesn't have radiative losses anyway, so we'll leave it like this. Now let's try something different. Let's try to see the effects of particle interactions. Let's suppose that there are collisions in your plasma. So if you have a phase space of V and R, this is actually a six-dimensional space, but I cannot draw a six-dimensional space, so I'm just drawing it in 2D. But suppose you have a box in this six-dimensional space with a group of particles at time t. Then you follow those particles, and there are no collisions in this system. Then with time this will deform into some shape, and the shape, the new volume will be that modulus of J times this. This is the new one at time t plus dt. Actually, we saw that J is equal to 1, so this is just the same volume, right? And all the particles keep inside it. So there are no collisions. The distribution function is constant with time, so it doesn't change. But if you do have collisions in your system, so this is again V with R, then it may happen that some of the particles that were in the original box will, through collision, be diverted to some other direction. So you lost this one, and there may be some other particles that are entering the new volume because of their own collisions. So you don't have conservation of the distribution of particles in this case. So how can we write Boltzmann equation in this situation? First, let's define this quantity here, delta F. This is R. Delta F, delta T. This will be our collision term times this. This will be the net gain or loss of particles of alpha particles as a result of collisions during dt time units in volume. If you follow what happens in volume D3R, D3V. Okay, then if you use delta F, delta T in equation 5.6, where is equation 5.6? 5.6 is this. So instead of 0 here, we'll now have this collisional term. So the difference between the distributions is the collisional term. In equation 5.6. So now we have F alpha R prime V prime T plus dt minus F R V T D3R D3V is equal to the collisional term. Now, if you follow all the derivations that we did before to get to equation 5.8, using that collisional term, it will appear in the right-hand side. equation 5.8 becomes the new form of Boltzmann equation is this. Or, in the reference moving with the element, you have this notation. Now, this is just a generic term. We don't know how it looks like. So you may have different expressions to represent this collisional term. One of the most famous ones and simplest one as well is the relaxation model. This is really a toy model for the collisional term. This is by Crook. So let f not function of r and v be the distribution function of local equilibrium. If we're in an equilibrium, then it's not a function of time. In the absence of external forces, you have your distribution RVT decaying towards this equilibrium distribution. So it reaches a steady state if you don't have any external force as a result of collisions. So in this model, you may write the collisional term like this: minus f alpha minus f alpha naught over tau. So this is perhaps the simplest possible form for the collisional term. So I have the difference between the distribution at time t and the difference and the distribution at the equilibrium, the asymptotic value of the distribution. And tau is a relaxation time. It's the time it takes to reach this equilibrium. It's usually of the order of the mean time between collisions. If the system is in equilibrium, you just have f alpha equal to f alpha naught. And the collisions do not change f, okay? So what's the interpretation of this? How can this be considered a realistic, or is it a realistic collisional term? What is it representing? Let's try to answer this question. Interpretation. In the absence of external forces, that is, you don't have acceleration, right? And space gradients, that is, you have this equal to 0. Then equation 5.23 becomes, what is 5.23? Let's see. 5.23 is just this one. So we don't have this. This is actually like this, right? You don't have this, and you don't have this. So you have just an ordinary differential equation. It's actually a partial differential equation because f is a function of more than one variable, but it will behave like just an equation with derivative in time. So we may solve it with techniques of ordinary differential equations, and that's the good thing about this model. It's easy to solve, and we can solve Boltzmann equation. So I'll just write it in the standard form for a first order linear differential equation. Have it like this. And a non-homogeneous term like this here. So this is just the same thing. And to solve this equation, we may use an integrating factor. Integrating factor, you know this from linear ordinary differential equations. And when you have it like this, the classic integrating factor is just the exponential of the integral of your integrating variable, and this term, 1 over tau, right? The coefficient of this term. So it's like this. So if you multiply this equation by this, t over tau plus et over tau, you multiply all terms by this. Not right a number for this equation. Then we may write it like this. So now the equation can be integrated easily. Let's see. So yeah, this is just this derivative. The rule of product here will be like this. And now we just integrate in time. So integrating in time, you get integration of this in time is equal to the integral of the right-hand side plus a constant. In this case, the constant will actually be a function of velocity. Why? Because you do have an f function which is a function of velocity and time. So remember this. We have, this is actually like this. Why is it not a function of space? Because we're considering that we don't have spatial gradients. We are in a homogeneous plasma. So, homogeneous. Okay, so the integrating constant will actually be a function of E. If you derive this expression with t, then it goes away. So from here, let me see. What is this? Okay, so the integral of this derivative will be just this term, and I can remove this from here because f is not a function of t. F0 is not, right? Where is this at? Okay, this is not a function of t. This is the asymptotic value, so I can remove it from the integral. So it gives you an expression like this: t over tau f alpha equals f alpha naught tau integral of e t over tau dt plus this function. And this is just this expression e t over tau over 1 over tau. This is the integral of the exponential, and I can cancel these two terms, and we got f of vt equal to this plus a constant e minus t over tau. This is strange. It looks like an x. It's tau. Okay, to compute the constant at t equal to 0, we have f v0 equal to this, right? So we get c equal to this, and then I will just use this in here and obtain f vt is equal to f. Oh, this is a function of v. This is no longer a function of t because this is the equilibrium value, and I have the constant here minus this e minus t over tau. This can be interpreted as the difference between f and f alpha and f alpha 0 decays exponentially by this term. It decays exponentially with time at a rate governed by the rate of collision, which is 1 over tau. So this is the, so we have this quantity here, which is the frequency, collisional frequency of relaxation, or relaxational, I don't know how, I think it's relaxational, let's say just collisional frequency of relaxation, okay, of relaxation. The applicability of this model, since it's a very simple collisional term, its applicability is also limited, and it's limited to weakly ionized plasmas, where only collisions of charges with neutral particles are important, and collisions between particles of the same mass. Usually, the relaxation times for velocity and moment are different. Different from the relaxation times of thermal energies, for instance. So we need a different model for this. It's too simple. It's too simplistic to say that the relaxation time is the same for all species and for velocity and thermal energy. So usually we need a more elaborate term. But this will do in simple cases. It's initial guess for the collisional term. It's not a bad one. Now, let's talk about, finally, about the Vlasov equation. What is the Vlasov equation, and what is its relation with Boltzmann equation? Vlasov equation. It's actually just Boltzmann equation when you have pick up equation 5.8. Let's see, where is 5.8? Boltzmann here. Okay, you get this equation, Boltzmann equation, and you use substitute by F over m for acceleration. So acceleration is force over mass, mass of alpha particle, and F is some external force, right? So, but in Vlasov equation, we'll use Lorentz equation for the force. It's just that. So I'll represent acceleration as force over mass, and then use Lorentz force for F. Okay. Using A equal to F over mass in equation. So we're no longer considering collisions, all right? So forget about collisions now. We're using equation 5.8 with this, and F will be an external force plus Q, the Lorentz force. I had said that it's Lorentz force, but there's space for an external force here, where the second term is the Lorentz force. Oh, let's say the mean Lorentz force. Mean Lorentz force computed in a volume element. All right, therefore, if you use it like this, you can write equation, the Boltzmann equation, in this form. So we have a charge of alpha particles, and this index I is just the index for each charge, each particle. Where EI and we have EI and BI, right? And BI are obtained by solving Maxwell's equations. So we have Maxwell's equations. Oh, sorry. Yeah, that's it. This one as well. The curl will be equal to minus del B I del T, and this one as well. What are rho and J? Where is J? No, rho. Where is J? J. Oh, okay, J is here. In curl of B, where is the curl of B? I've got one. Oh, here. So you have J and what else? Rho is here. So with rho equal to the sum of alpha particles Q and O. So it's the charge density for each species, which I may write like this. And J is Q alpha to it's the current. So it's this times the mean velocity in the element for alpha particles. You may check that it may be written like this. So you actually have to solve all these equations at each time step. If you're solving this numerically in a computer, then in each time step you have to solve all these equations for each element. So you don't have collisional terms here, but the collisional term, the absence of collision term, is supplied by the effects of the Lorentz force. So it may relate different elements here. It adds a level of complexity to these equations. So you have to solve all Maxwell's equations and all this equation and these equations as well. So it's really, really heavy, depending on the number of elements you have in your phase space. So when you look at these equations, you see you have an equation for F, you have equation for electric field, you have an equation for rho here, an equation for J, and we'll use J to obtain B, and then you must satisfy all these equations, and then you may ask yourself, wait a minute, how can I find V? What is the value of V? There is no equation for V, so there is something missing here. Actually not, because remember that in this formalism, V is an independent variable. So your independent variables are position, time, and velocity. So F is a function of V. So no need to worry about it. You don't need an equation for V. For each V, you have a value for this equation. You may change V from minus infinity to plus infinity and have an equation, a different equation like this for each one of them. Okay, and this is the end of chapter 5.